Hi, my name is Daniel. I work at Meta. I work on profiling and scheduling, and we'll be talking about schedulers today. So first, we'll start kind of ease our way into scheduling. So what is scheduling? Obviously, we have tasks that run on a machine. We have a kernel, and we have this thing called a scheduler, and it decides where your tasks run. So you can see our tasks are little green circles, and our scheduler is the blue box. Its job is to place tasks on certain CPUs. It also determines how long tasks are allowed to run for. But why do we care about scheduling in the first place? So let's say, we're playing a game and we want to start compiling a kernel to make a change. You do that and your game starts to stutter. It's not fun playing at 12 FPS. But if we run a custom scheduler, we can start to creak our performance back up, get 19, 20, and maybe get a few more FPS out of it. So this is just an example of different schedulers behave differently under load and with interactive task running. Okay, stop. So why do we care about schedulers? Modern hardware has changed a lot. In the past, we had very simple hardware with no hyperthreads and very simple cache hierarchies. But now we have hardware with multi-socket, multi-NUMA nodes, multi-caches, big cores, little cores. Things have just gotten more complex. We have stacked workloads. You have your applications, you have sidecars, and all these things need to be have scheduling that makes sense for what you're trying to achieve with your application. And also, scheduling is really hard. There's only a small number of people who work in the kernel on scheduling, and in general, it's not a very accessible field, but we want to make that better. So we're going to talk about how to build schedulers with BPF, some of the existing SCEDX schedulers that are being developed, and some of the problems that scheduling at scale. So first, what is SCEDX? It's a pluggable BPF interface into the kernel scheduler that allows you to run a BPF program as a scheduler. It's safe. It automatically exits if you cause tasks to stall, so it won't crash your kernel. And it allows for rapid iteration time. So you don't have to reboot, recompile your kernel. You can just load a BPF program as a scheduler, make some changes, kick it out, and it shortens your overall iteration time. So how do we extend the kernel with BPF? I'll give a high-level overview, but the best way to learn is actually look at the code. We'll be covering some simple schedulers, which are very simple implementation. And I'm going to assume that you have some knowledge of BPF. And overall, our goal is to understand the building blocks of how to build a scheduler. So we start with BPF building blocks. BPF has a number of things that have been developed to help us build schedulers. And those are BPF helpers, kfuncs, maps, CPU masks, and structops. So what are BPF helpers? They're basically found in every type of BPF program you've ever seen. If you've ever looked at some BPF code, they're used for tracing, networking, security, monitoring, and it's kind of almost like a syscall interface into the kernel, but it's just a standard set of APIs that don't really change that can be called from within your BPF program. So for example, if you've ever seen a stack that gets collected by a BPF program, it's called with this BPF get stack function. Kfuncs are similar to BPF helpers, but they're not necessarily a stable interface, and they can be restricted per type of BPF program. So if you have a tracing function, it may use a set of kfuncs that are different than a BPF helper, but they're kind of extensively used in SCEDX, which we'll go over in a little bit. But the kernel docs have really good documentation for kfuncs in general. Next, we have BPF maps. So BPF maps are how you use storage within BPF. Traditionally, BPF didn't have a great memory model. It's being developed and being worked on actively with BPF arenas. So traditionally, the solution was throw everything into a map. It works, I guess, but there's different types of maps that you'll see being used in BPF programs. Next, we have BPF CPU mask. So it's the BPF version of the struct CPU mask in the kernel. And these are used for things such as idle CPU tracking, topology awareness, or affinity groups. And you can do things with like a CPU mask that like set a bit that represents a single CPU in your bit mask, or CPU mask, sorry. And just to give an example of how to use a BPF CPU mask, there's actually some k-funcs that are used as helpers to create them. So you can see in blue, we have a BPF CPU mask create function, which creates our CPU mask. We can then set a CPU using BPF CPU mask set CPU to set a bit for a particular CPU. And we can do all sorts of bitwise operations such as ANDs, ORs, XORs. So you'll see, if you look at any scheduler code, you'll probably see BPF CPU masks being used extensively. Finally, we have struct ops. So what are struct ops? Struct ops are basically a way to implement a function interface in the kernel using BPF. So here we have in blue our struct BPF example ops as our interface, and we have two functions, foo and bar. So you will implement a foo function in BPF and a bar function. So what does this look like in BPF? There's a little bit of macros here, kind of go over that. In blue, you can see struct ops / foo, so that's telling you this macro is implementing the foo interface. And we have foo impl, and same thing with bar. And then down at the bottom, we have where we actually define our interface in BPF as example 1, where we set our foo equal to foo impl and bar equals to bar impl. The void star casting is just kind of a hacky workaround for the verifier. So it's kind of one of the not so, it's BPF. So, so how do we take our BPF program or struct ops program and load it into the kernel? So libbpf generates some nice skeletons for us to handle this. So you could load your skeleton with a struct ops example open, and then do any setup, and then load it into the kernel using struct ops example load. So how does SCEDX use it? Well, it actually uses its own interface called SCEDX ops, and there's a number of functions here. So it's basically the same way. There's some macros to make the definitions a little bit more pretty. You can also see at the bottom we have our name as simple, so you can define other properties on your scheduler, such as like configuration bits, things like that. And one thing to note is this is only a subset of all the available methods. You don't have to implement them all, though. Okay. There's one more thing that I didn't cover that we need to know is how do you actually run a task with your scheduler? And we use these things called DSQs or dispatch queues. And there's one global DSQ, which is a FIFO DSQ, and there's CPU local DSQs. But you can also create your own scheduler-specific DSQs using SEX BPF create DSQs. And once again, that's a k-func that's creating your DSQ. And besides FIFO, you can also use priority queues as well, but you can't have a DSQ be both at the same time. So how do DSQs actually dispatch task and run the task? So a CPU always executes a task from its local DSQ first. So the order of operations is consume from your local DSQ, consume from the global DSQ, and if that doesn't have any tasks to run, it calls the dispatch function. So we'll take a quick overview of our different ops and kind of go over. our simple scheduler. So you can follow along at the GitHub link here to the simple scheduler, and there will be a link later if you want to look it up later. But first we have kind of an init and exit hook for when your scheduler gets loaded into the kernel. And this allows you to create different maps that you'll need for, let's say, checking stat or measuring statistics, or just any maps you would need to create to run your scheduler. There's also lifetime hooks. So these are callbacks on task states, like when a task becomes running, you can run a BPF program, or if it comes off CPU, or if the task is being enabled to be scheduled by SREcon24. Finally, we'll get to the more interesting and more important ones. The first one being select CPU. So select CPU can kind of do two things. It can dispatch to a DSQ, or it can return a CPU as a hint to the scheduler of this should be the preferred CPU to run. So visually, we can see that a task is waking up. It goes through select CPU in the BPF scheduler. And here's our options. We can dispatch to our local or global DSQ, or we can return our CPU value, which then gets passed to the enqueue method. So following our simple scheduler, here's our simple implementation where we basically set up a default CPU with a kfunc, and we dispatch to our local DSQ, or we return our preferred CPU. So not too complicated, it's simple. So then let's talk about enqueue. So you can dispatch to a DSQ, or you can enqueue the task to the scheduler. And once again, going back to our graphic, it's a little easier to follow. So from enqueue, you can also dispatch into your global or local DSQ, or if you've created any custom scheduler DSQs, you can also dispatch into those DSQs. And our simple enqueue function is also rather simple. So we set up the v time, which is, and the time slice, which is like how long the task should run. And then we dispatch it into our scheduler created DSQ, shared DSQ, with SEX BPF dispatch vtime. So that's just dispatching using our vtime. So what happens when our CPU is ready to schedule? Just covering this once again, we have our local DSQ that we consume from, our global DSQ, or we can dispatch. So how does dispatch work? If our local DSQ is empty, we can dispatch to our DSQs or enqueue to the BPF scheduler. I think I duplicated this slide. Sorry about that. Right, so when dispatch is called, we can once again dispatch into our DSQs, our local or global DSQ, or we can consume from our scheduler specific DSQ. So that means basically you're consuming tasks that were enqueued previously during enqueue, and you're consuming those during dispatch. And our simple scheduler is actually really simple. All we need to do is consume from our shared DSQ that we created. So what have we learned so far? We've learned the basics of how to build a scheduler. We covered kfuncs, BPF CPU mass, strucops, and if you want to see a full example, there's the secsimple.bpf.c in the SREcon24 repo that you can follow along. It's like under 200 lines of code, so it should be pretty approachable. And here's a QR code if you're interested, which it'll be available later. So let's talk about some of the schedulers that are in active development. There's SEX Rustland, BPF-land, who are primarily being developed by a developer who works at NVIDIA. SEX LobD, which is being developed for interactive gaming workloads. SEX Rusty, which is a general purpose scheduler, and SEX Layered, which is a soft affinity partitioning scheduler. So SEX BPF-land and SES Rustland are really interesting schedulers in that they're designed for interactive workloads, And SEX Rustland actually makes scheduling decisions in user space. And it performs rather well. If you look at the SCEDX repo, there's a video of Rustland doing the similar type of demo of compiling a kernel and playing games and still being able to achieve 60 FPFs. And it does so by tracking interactivity of tasks by looking at context switches. So it stores information about how often a task voluntary context switches and uses that to determine if it's an interactive task or not. Next, we have SEX LAVD, which is a latency critical aware virtual deadline scheduler. In my opinion, it's one of the most interesting schedulers in SCEDX. It's being developed for portable gaming, and it uses ideas of looking at the task graph relationship and understanding which tasks should be scheduled based on which their wakers and wakees. It also has a really cool feature called core compaction, which if you're working on a portable gaming device, if you're not plugged into power, you want the game to last longer with the battery. So it uses this strategy called core compaction to kind of collapse all your workloads down onto a subset of cores. It's also P and E core aware, or big and little core aware, which is very interesting. And the scheduling algorithm for calculating the virtual deadline is also novel as well. There's SEX Rusty, which is NUMA aware and multi-CCX aware. It also does user space load balancing, and it's kind of a general purpose scheduler that has a lot of features that other schedulers don't have, such as load balancing. SEX Layered allows you to define soft affinity groups called layers. It's widely deployed across the fleet at Meta. It's used for several critical services, and we'll go into some more details. It actually uses JSON for its configuration, so we do kind of parse and handle JSON in the kernel. It's a method. And there's kind of three different ways that it operates. It can put tasks into what are called confined groups, which allows you to restrict tasks to only run on a subset of CPUs. But if your utilization is within a range, it allows the affinity group to grow. Grouped is very similar, but it also allows tasks to spill out onto idle cores. And then open just is kind of like spray task everywhere. So it provides a ton of flexibility in how you want your tasks to run. And there's also a huge number of different types of matches to how you can match a task into a layer. So for example, if I wanted to create a layer for my user ID to make sure that my tasks run faster, I could create a group layer. There's also frequency control as well with pretty much all the schedulers implement this via a kfunc as well, or right, so frequency control, if you're using the schedutil governor, the scheduler can actually set the frequency and performance of this. This is super important if you have workloads that you want to run at high CPU but not turbo boost, or if you want certain like CPU intensive tasks or threads to always be hitting turbo, you can use this to configure your scheduler. But it is a very complex config, and sometimes it feels like there's way too many knobs to be tuning to work with the scheduler. So it's kind of a bunch of hacks kind of built together that allow you to get some kind of quick wins, I would say. So one question people always ask is, can a BPF scheduler perform as well as an in-kernel scheduler? And the answer is yes. A lot of it comes down to keeping your cache lines clean. Even if there's more overhead in running BPF as you're scheduling, if you make wrong decisions, it's actually just as bad as the overhead of running BPF. And we find that with really complex workloads and architectures, you can actually get good performance gains. So I'm going to show some benchmarks in the next slide, but they're benchmarks. They don't mean anything. I just ran this on one of my like personal boxes of sysbench for MySQL default configuration. So once again, you're not running MySQL with sysbench on default configs because it doesn't matter, but here's some results. So we can see that BPF land actually has really good latency because that's kind of what it's designed for. During this benchmark, it didn't really saturate the machine. So that's, yeah, BPF land's going to do really well. EEVDF is the default scheduler in kernel 6.12, which I believe this was ran on. And then you can see some of the other schedulers, like if you don't run them with specific configuration, they may not perform as well. So here's just some like query throughput as well of transactions and queries. And you can see BPF land performed extremely well in that regard. So what are some of the challenges of deploying BPF schedulers at scale? We'll talk about some of those, including backporting, complex architectures, testing, observability, and just dealing with BPF in general. So kernel backports. Have a good strategy for upgrading your kernel. I spend a lot of time doing backports because SCEDX is a 6.12 feature, and backporting to like kernel 6.4 where stuff like doesn't work that great. The verifier is different. You'll be looking at verifier bugs all day, and then now you have to maintain like backward patch sets. It's not fun. So if you can avoid backporting, it's a good thing. Or you can wait 2 years for your team and org to determine, hey, maybe we should upgrade our kernel, and then we can use all these new features. So if you can, have a culture of like upgrading your kernel. It's just a piece of software like anything else that has bugs that needs to be updated. You can save yourself a lot of pain by updating the kernel. And going back to architectures. So when scheduling was easy and we had the unified caches, SMT maybe, hyperthreads, no big little cores, scheduling was not so hard. But now we have, let's say we have a 4 NUMA machine with 4 GPUs, a single Ethernet interface, and this is still a pretty simple machine compared to what you'll find in a lot of data centers. But let's say your networking team comes to you and says, hey, we want to run our network cards at basically full throughput because we're trying to pull down a lot of training data and we need to have things scheduled properly. So we want to keep NUMA 1 have less things run on it so that we can handle our packets much faster. And then you have, another team says, hey, we're trying to do our GPU inference on GPUs 1 and 3 because they're closest to the Ethernet card. So we don't want to do a bunch of cross NUMA, chat or like memory bandwidth utilization if we don't need to. And then you have another team who's like, hey, maybe we should do GPU training on these other GPUs because no one's really using them because the NUMA latency is so bad. So scheduling starts to become this really distributed systems problem, all on a single machine. So I think that's one of the things that interests me about scheduling is that I've given up on trying to work on many systems because there's enough complexity on a single machine to make good scheduling decisions. So correctness testing. How do you actually test that your scheduler is correct? It's not really easy. I've talked to some other people who worked on schedulers. They're like, yeah, it sort of works on my machine. It's like, okay, cool, let's deploy it across the fleet. That's not a great way to do testing. So you can test in prod, that's bad. Or what we've been trying to utilize is like BPF trace to actually do some testing. So like if you're trying to restrict or make sure the scheduler is running a certain task on a subset of cores, you can actually write a BPF trace script that will make those assertions and like kill itself if tasks run on cores that it's not supposed to. It's kind of black magic, I would say. Performance testing. A lot of the testing that we use for testing a scheduler is just like SREcon24. It's a really great tool for doing just random workload benchmarks. But you also should be testing like workload specific things. So if you have a specific workload that you're trying to tune your scheduler for, testing your workload is also really important. But yeah, you can see some SREcon24 output. We look at like BOGO ops per seconds, and there's like many different SREcon24 tests that you can run. So how do we observe schedulers? The schedulers themselves have a set of stats and metrics that they emit. And we also use some scripts, like BPF trace scripts, for various types of monitoring. So you can get like distributions of your latency. There's this one in particular is for like DSQ latency. So you can see the distribution of how long tasks are sitting in DSQs. And then down here in the bottom, you can see basically the average latency per DSQ. You can also use Perfetto for visualizing scheduler traces. There's some helper scripts that allows you to use ftrace, but this allows you to dive down and actually look at what scheduling decisions were made in a kind of traced format as well. System metrics are also very important to look at. So context switches, LLC hit ratio, your request queue delay, IPC. One of the things that we sort of noticed is if you put all the noise into a subset of cores, your applications actually perform better just because there's not so much crap thrashing your caches. So having a good way to monitor your system metrics and observe those over time is super useful. So what's the future direction? So we want to build composable schedulers to make it easier for people to write their own scheduler. There's a lot of like copy-paste code in BPF that's kind of not great. So you end up having to implement different things. So for example, SEX Rusty implements load balancing. Well, we kind of want all scheduler to have load balancing, but we don't want to copy-paste all that code. So there's a lot of work that needs to be done to refactor the code base to make it easier to just kind of plug and play to create new schedulers. Another interesting development that will probably happen over the next year or so is concurrent scheduler support. So you can think of it kind of like loading multiple BPF schedulers into the kernel. Right now, the restriction is you can only load one, but you could imagine a case where you load a specific scheduler for a C group or container that works well for what that container is supposed to do. There's also someone who's been working on writing a scheduler using Java. So you can write Java code that compiles down into BPF and implement a scheduler. I've also joked with Alistair, the BPF trace creator, about creating a scheduler in BPF trace. Is like, well, why not? It's a crazy idea, but maybe. So in conclusion, we've kind of covered how to build a scheduler. We've talked about some of the challenges, but most importantly, we need more people who are interested and want to work on schedulers. The core development team of people who actually work on developing schedulers is like a handful of people, but there's room for anyone who's interested. So I would say the worst thing you could do is think that you're not capable of developing a scheduler, because if you can manage complex runtimes, you can probably write a scheduler better than me, because we just kind of sometimes wing things. There's office hours that get held every week, and if you join, ask questions, people will be very willing to help you out. And yeah, I think that's pretty much it. I guess, yeah, thanks to Meta, my manager, various other people, I guess. The BPF maintainers are also really great to work with. Yeah.